Hello, friend. Welcome back, and if you're here for the first time, welcome. You've found a quiet corner of the universe. Pull something warm around you, close your eyes if you'd like, and just listen. Tonight or this night, wherever you are, we're going to go somewhere that no human being has ever returned from. Somewhere that swallows light. Somewhere that bends the very fabric of what we call now. We are going to the edge of a black hole. And we are going to ask the strangest question physics has ever dared to whisper out loud. What happens to time when there is no more space left to hold it? Before we begin drifting, if these quiet journeys through the cosmos bring you something, a little peace, a little wonder, a softening of the day, you might like to stay a while. You can gently tap the like button if this feels like the kind of place you'd return to. Subscribe if you'd like the next quiet night to find you again. And ring the little bell not for noise, but so that these stories can drift to you when you need them most. That's all. Now, let's go. There is a clock sitting on a table in Bern, Switzerland. It's an ordinary mechanical clock, the kind you could find in any watchmaker's window in 1905. Brass gears, a slow, steady tick. Reliable as a heartbeat. A young man named Albert Einstein used to stare at clocks like this on his way to work every morning, past the great clock tower at the center of the city, its iron hands sweeping in perfect arcs across its white face. He worked in the patent office. He spent his days reviewing other people's inventions. But what occupied his mind, what truly lit something deep and restless inside him, was a question he had been carrying since he was 16 years old. What would the world look like if I were riding on a beam of light? If you could travel alongside a ray of light, moving at the same speed? Looking back, what would you see? The light would appear to stand still, frozen, a wave suspended in space like a painting of movement rather than movement itself. That image haunted him. Because if light could appear to freeze, what did that mean for the clock tower he passed each morning? What did that mean for time? We tend to think of time the way we think of breathing. It simply happens. It moves at the same rate for everyone, everywhere, always. 1 second is 1 second whether you are sitting still in a chair or hurtling through space at tremendous speed. The universe, we assume, keeps a single clock. And that clock applies to all of us equally. This assumption is so deep, so woven into the texture of ordinary life, that questioning it feels almost childish. Of course, time is the same everywhere. We all age. We all feel the minutes pass. Tuesday follows Monday for everyone. But Einstein was never afraid of feeling foolish in the presence of a beautiful question. And so, in the same year that he submitted 3 papers that would rewrite physics forever, he arrived at something that sounded more like philosophy than science. Time is not fixed. Time is a river, and depending on where you stand, how fast you're moving, or how close you are to something enormously heavy, that river flows at a different rate. He called it special relativity. And then 10 years later, he extended the idea into something even more, sweeping something that brought gravity into the picture, something he called General Relativity. And buried inside those quiet mathematical equations, written not in a great university laboratory, but in a small apartment mostly late at night, was a prediction so strange that even Einstein himself was unsettled by it. Near an object massive enough, time doesn't just slow down. It slows down measurably, verifiably, permanently. And if the object were massive enough, if gravity were strong enough, time could in theory slow towards something that looks from the outside almost like stillness. Now here is a small thing worth pausing on, because it reveals one of the most common misconceptions people carry about black holes and time. When most people hear that time slows down near a black hole, they imagine something cinematic, a traveler approaching the edge feeling themselves moving in slow motion, their heartbeat stretching, their thoughts becoming thick like honey. But that's not quite how it works. The traveler doesn't feel slow. They feel perfectly normal. It is only to someone watching from a safe distance far from the gravity where time flows freely that the traveler appears to slow down, appears to stretch, appears to hover at the edge of the unknown like a photograph of a falling thing. This is the extraordinary subtlety of gravitational time dilation. It is not something you feel from the inside. It is something the universe does to you relative to others. 1 second feels like 1 second to you always. But those seconds, when measured against someone else's clock somewhere else in space, may be worth far, far more or far, far less. Have you ever had the feeling that time was moving differently than usual? A long, quiet afternoon that stretched like a summer, or a morning that vanished before you had time to hold it? What if the universe were doing something similar? Not as metaphor, but as physics. We now know with remarkable precision that Einstein was right. In 2004, physicists used an instrument called a hydrogen maser, one of the most accurate clocks ever built, and flew it above Earth on a rocket. The clock at altitude away from the heaviest pull of Earth's gravity ticked slightly faster than an identical clock left on the ground, slightly, by only a few microseconds per day. But slightly is enough. The GPS satellites orbiting our planet right now, the same satellites that guide your phone when you're lost in an unfamiliar city, must account for Einstein's prediction every single day. Without corrections for both special and general relativity, GPS coordinates would drift by roughly 11 kilometers over the course of a single day. The technology we use to find a coffee shop or navigate home from the airport only works because a man in 1905 sat quietly and asked a ridiculous question about a clock tower. Time is not a background. It is not a stage that the universe performs upon. Time is part of the fabric itself. It curves, it bends, it moves differently in different places. And if that is true near Earth, near something with only modest gravitational pull in cosmic terms, then near a black hole, where gravity becomes something almost unimaginable, what happens to time is not a metaphor. It is not a dramatic flourish. It is the most literal thing in physics. Let's drift for a moment into the idea of what gravity really is, because this matters for everything that follows. We grew up with a simple picture. Gravity is a force. The Earth pulls you down. The sun pulls the planets around it. Mass attracts mass. Newton described it beautifully, and for 300 years, that description was enough. But Einstein's picture is different, and stranger, and somehow more beautiful. In his view, there is no force called gravity. There is only the shape of space itself. Imagine you have a large rubber sheet stretched tight and flat. Now, place a heavy ball in the center of it. The sheet dips, curves, and if you place a smaller marble nearby, it doesn't get pulled by a force toward the heavy ball. It simply rolls along the curvature, following the geometry that the heavy ball has created. That is gravity. Not a force reaching across space, a curve in the shape of space itself. And time, it turns out, is part of that shape. The heavier the object, the more dramatically it curves space-time. The more dramatically space-time curves, the more slowly time passes in that region. A mountain moves through time slightly more slowly than a valley, not enough to notice, not enough to matter in a human life, but measurably, provably, genuinely more slowly. And in the extreme case, in the case of a black hole, where the mass of an entire dead star has been compressed into a region smaller than a city, smaller than a town, in some cases, smaller than a single point, the curvature becomes something that breaks the imagination. There is a word that physicists use quietly and carefully when they try to describe what happens at the center of a black hole. The word is singularity, not darkness, not emptiness, not a very small, very dense thing, a singularity, a point at which the equations of physics, the same equations that correctly predicted GPS errors, that correctly describe Mercury's orbit, that correctly guided spacecraft across billions of miles of empty space, simply stop working. The math doesn't give a large answer, it gives an infinite one. And infinity in physics is not a number. It is a sign that the model has broken down, that you have gone somewhere the map doesn't cover. This is where time doesn't just slow. This is where the question of what time even means becomes genuinely unanswerable. But we are getting ahead of ourselves, drifting too deep too fast. Before we reach the singularity, before we stand at the edge of that final horizon and look in, we need to understand how a black hole is born. Because black holes are not created out of nothing. They are not conjured by darkness or designed by some cold logic of the universe. They are made from the most beautiful, most violent, most profound act in all of astrophysics. They are made from the death of a star. And that story, the story of how something so bright, so warm, so ancient and familiar as a star becomes something that can stop time, begins not with darkness at all. It begins with fire. So let's go back. Let's go back billions of years to the moment when a star much like our own sun, but many, many times more massive, began to lose its long battle against gravity. Because that story changes everything about what we think we know about time, about endings, and about what the universe does with the things it can no longer hold. 4 billion years from now, our sun will begin to die. Not violently, not dramatically. It will simply run out of the thing that has kept it burning since before the Earth existed, and it will swell slowly into something enormous and red and ancient, before collapsing quietly into a cold, dense ember the size of a small planet. Our sun will die gently. But there are stars in this universe that do not die gently. There are stars so massive, so furiously alive, that when they finally exhaust their fuel, the death is not a fading. It is a detonation, an implosion so total, so absolute, that not even the laws of physics as we understand them can fully describe what comes next. And inside that implosion, inside the collapse of something that once burned brighter than a billion suns, something extraordinary happens to space and to time. Let us begin there. Let us begin with fire. To understand a black hole, you must first understand what a star actually is. Not the romantic version, not the distant light in the night sky, fixed and permanent and serene. The real version. A star is a war. It is a continuous violent battle between two of the most fundamental forces in the universe. Gravity pulling everything inward and the outward pressure of nuclear fusion pushing back. Every second that a star shines, it is detonating hydrogen atoms in its core, fusing them into helium-releasing energy on a scale that makes every nuclear weapon ever built on Earth look like a match being struck in a hurricane. Our own sun converts approximately 600 million metric tons of hydrogen into helium every single second. Every second. It has been doing this for roughly 4.6 billion years. And it still has fuel for another 5 billion or so to go. But here is the critical thing that balance fusion pushing out, gravity pulling in, is only possible as long as the fuel lasts. When the fuel runs low, the balance shifts. Gravity begins to win. Now for a star like our sun, this losing of the battle is gradual and relatively quiet by cosmic standards. The outer layers swell, the core contracts. What remains is called a white dwarf, dense cooling, roughly the size of Earth, but containing the mass of the sun. A white dwarf is held up, not by nuclear fusion, but by something called electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain point. It is a strange and subtle thing, this resistance, but it works and it holds. For stars that are a little more massive than our sun, say 8 to 20 times as heavy, the story goes further. The core does not stop at a white dwarf. It collapses deeper past electron degeneracy until protons and electrons are forced together to form neutrons. What remains is a neutron star, an object roughly the width of a city, perhaps 20 kilometers across, but containing more mass than our entire sun. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. 1 billion tons in a teaspoon. But for the most massive stars, those that dwarf even these numbers, stars 15, 20, 40, or even 100 times the mass of our sun, even neutron degeneracy is not enough. Gravity wins completely. And what happens next is the most extreme physical transformation the universe is capable of producing. Picture a star. Imagine something so large that if you placed it where our sun sits, it would extend past the orbit of Mars. Imagine it has been burning for perhaps 10 million years. which sounds long to us, but is quite short by stellar standards. Massive stars burn through their fuel quickly because their gravity demands so much more fusion pressure to stay balanced. They live fast and bright and brief. For most of its life, this star burns hydrogen into helium. When the hydrogen runs low, it begins fusing helium into carbon. When that runs low, it begins fusing carbon into neon, then oxygen, then silicon. Each stage is faster than the last, because each stage releases less energy and requires more compression and temperature to sustain. The star is in a sense eating itself through a sequence of desperate compromises. When the core finally reaches iron, the star stops. Iron is the end of the road for nuclear fusion. Fusing atoms lighter than iron releases energy, but fusing iron requires energy. It takes more than it gives. The furnace that has held the star up for millions of years simply cannot burn iron. The fuel is gone. There is nothing left to push back. And in a moment, not gradually, not slowly, but in a fraction of a second, the core collapses. This is what astronomers call the core collapse, and the speed of it is staggering. The inner core, which was perhaps the size of Earth just moments before, collapses to roughly 20 kilometers across in less than a second. The outer layers of the star, suddenly having nothing to stand on, fall inward at a quarter of the speed of light. They hit the newly collapsed core, and they bounce. That bounce, the shock wave from the collision of infalling material with the incredibly dense collapsed core, is what we call a supernova. A supernova is not simply a large explosion. It is the largest explosion that routinely occurs in the universe. In the first 10 seconds of a supernova, more energy is released than our sun will release in its entire 10 billion year lifetime. In the weeks following the explosion, a single supernova can outshine an entire galaxy of hundreds of billions of stars. In 1987, astronomers detected light and neutrinos from a supernova in a neighboring galaxy called the Large Magellanic Cloud, roughly 168,000 light-years away. Despite that inconceivable distance, the burst of neutrinos from that one dying star was detectable here on Earth underground, using instruments that had been built to study something else entirely. The universe itself rang like a bell. Supernovae are also the reason you exist. The carbon in your body, the iron in your blood, the calcium in your bones, these elements were not created in the Big Bang. They were forged in the cores of stars and scattered across space in the violence of supernova explosions. Every atom heavier than hydrogen and helium in your body was made inside a star that died before our solar system was born. You are in the most literal scientific sense made of dead stars. Does that feel strange to know that the iron moving through your veins right now was once burning inside a star that exploded billions of years ago, and that the shock of that explosion eventually seeded the cloud of gas and dust that became our sun, our Earth, and you? But not every supernova leaves behind the same thing. For moderately massive stars, what remains after the explosion is a neutron star, that impossibly dense spinning city-sized remnant we mentioned earlier. Some neutron stars spin hundreds of times per second and emit beams of radio waves like cosmic lighthouses. We call those pulsars. The first one was discovered in 1967 by a graduate student named Jocelyn Bell Burnell, who noticed a strange, perfectly regular radio signal repeating every 1.33 seconds. Her supervisors initially nicknamed the signal LGM1 for Little Green Men, because the regularity seemed almost engineered. It was not engineered. It was a neutron star spinning with a precision that put our best atomic clocks to shame. But for the most massive stars, those that collapse completely beyond even neutron degeneracy, nothing bounces back. The core does not stop at neutron star density. It keeps collapsing. It falls through every barrier the universe might have offered, past every threshold of resistance into something that has no size at all. Gravity crushes the core to a point of infinite density. And in doing so, it creates a region around itself where the curvature of spacetime becomes so extreme that the escape velocity, the speed you would need to reach to escape the gravitational pull exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing can escape. The black hole is born. Here is something worth pausing on because it is a misconception that trips up even careful thinkers. A black hole is not a hole in space. It is not an absence. It is not emptiness. It is mass. Enormous concentrated real mass packed so tightly that space itself has curved around it like a drain. If you were to replace our sun with a black hole of exactly the same mass, the planets would continue orbiting in exactly the same paths. Earth would not be sucked in. Mars would not spiral inward. The gravitational field at our distance from the sun would be identical to what it is now. The only difference would be that the light would stop. The warmth would vanish. And at the center of the solar system, where a star once burned, there would be only a region of space from which nothing returned. Black holes are not cosmic vacuum cleaners. They do not actively pull things in with extra hunger. They are simply places where the ordinary rules of escape no longer apply. But as you get closer, truly close, the rules change in ways that are far stranger than any vacuum cleaner could manage. The first person to calculate that Einstein's equations predicted a region from which nothing could escape was not Einstein himself. It was a German physicist named Karl Schwarzschild. In 1915, while serving as an artillery officer on the Eastern Front during World War I, Schwarzschild read Einstein's newly published papers on general relativity in the trenches. And in the brief spaces between combat between the cold and the noise and the dying, he solved the equations. He found an exact solution to Einstein's field equations, a mathematical description of the spacetime around a perfectly spherical, non-rotating mass. And buried in his solution was a strange term, a radius at which everything broke down. A boundary below, which the math suggested space and time, behaved in ways that seemed to violate common sense. He sent his solution to Einstein in a letter. Einstein wrote back astonished that he had not believed an exact solution was possible. Schwarzschild died a few months later from a disease he contracted at the front. He never knew that the radius he calculated would one day be named after him, the Schwarzschild radius, and that it would become one of the most important numbers in modern astrophysics. Every black hole has a Schwarzschild radius. For our sun, it would be approximately 3 kilometers. Compress the entire mass of the sun into a sphere 3 kilometers across, and you have a black hole. For Earth, the Schwarzschild radius is roughly 9 millimeters, about the size of a marble. Every object has one. The difference is simply that in ordinary objects, the mass is spread across a volume far larger than its own Schwarzschild radius. So, the effect never manifests. It is only when collapse drives the mass inside that radius that something fundamentally new appears in the universe. And that something new has a name we will carry with us for the rest of this journey, the event horizon. It is not a surface you could touch. It is not a wall. It is not a visible boundary gleaming in the dark. It is the point of no return, a threshold in space defined purely by geometry, by the mathematics of curvature beyond which the future has only one direction inward. What happens to light there? What happens to matter? What happens to time? Those questions are not simple. They are not answered by intuition. They require us to go further, to stand at the very edge of what physics can describe and look in. And that is exactly where we are going next. Because the event horizon is not just a boundary in space. It is a boundary in time. And understanding why changes everything about how we think about the universe and about the nature of now. We just watched a star die. We watched gravity win its ancient war against fire, watched a core collapse in less than a second, watched a shockwave tear through the outer layers of something that had burned for millions of years and scatter the remnants of that burning across the galaxy like seeds. And at the center of all that collapse, something new came into being. A region of space so curved, so extreme, that the rules we use to navigate ordinary reality no longer apply. But to truly understand what that means, to understand why time behaves the way it does near a black hole, why it slows, why it bends, why it might, at the very limit, cease to have meaning at all. We have to go back to the equations that first predicted this was even possible. We have to go back to Einstein, not the icon, not the poster on the wall with the wild hair and the knowing smile. The young man, the one who was told more than once that he was not suited for academic work, the one who failed his entrance exam to the Swiss Federal Polytechnic on his first attempt, the one who, after finally graduating, could not get a university job and spent years reviewing patent applications while quietly rewriting the foundations of physics in his spare time. That Einstein. Because the story of how he arrived at his understanding of time is not just a scientific story, it is a human one. In 1905, Albert Einstein was 26 years old and working as a third-class technical examiner at the patent office in Bern. He had no laboratory, no research assistants, no funding, and no academic position. What he had was time-long quiet hours at a desk, where the work was methodical and undemanding, and a mind that refused to stop asking the questions that other physicists had decided were either unanswerable or unimportant. That year, he published 4 papers. Each one individually would have secured a physicist's reputation for a lifetime. Together, they changed physics permanently. The first explained the photoelectric effect, the observation that light can knock electrons off metal surfaces, and in doing so, laid a cornerstone of quantum mechanics. That paper eventually won him the Nobel Prize. The second explained Brownian motion, the random jittering of particles in liquid, and provided the first real mathematical proof that atoms exist. The third paper was titled in translation, On the Electrodynamics of Moving Bodies. It is what we now call special relativity. And the fourth, a 3-page follow-up to the third, contained perhaps the most famous equation in human history, E equals mc squared. We will come back to that equation because it matters more to our story than most people realize. But first, let us sit with special relativity because it is the foundation upon which everything that follows is built. The central problem Einstein was trying to solve in 1905 was not exotic or abstract. It was, in a sense, embarrassingly practical. The equations that described electricity and magnetism developed by James Clerk Maxwell in the 1860s predicted that electromagnetic waves, including light, travel at a specific speed, approximately 300,000 kilometers per second. Not approximately that speed depending on how fast the source is moving. Not that speed relative to something. Simply that speed as a constant of nature. But this created a problem. In Newtonian physics, the physics that had governed science for 200 years, speeds add. If you are on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, the ball moves at 150 kilometers per hour relative to the ground. Everyone agreed on this. It was intuitive obvious and had been confirmed by centuries of experience. So, what happened when you applied the same logic to light? If light always travels at the same speed, regardless of the motion of its source, then either Maxwell's equations were wrong, or Newton's rules about how velocities add were wrong. One of the 2 pillars of classical physics had to give. Most physicists faced with this choice looked for a way to patch things up. Perhaps there was some invisible medium through which light traveled, and the speed was constant only relative to that medium. They called this hypothetical medium the ether. Experiments were designed to detect it. The most famous, conducted by Albert Michelson and Edward Morley in 1887, found absolutely no evidence that it existed at all. The ether was not there. Einstein took a different approach. He did not try to save the old framework. He asked, what if the constancy of light speed is simply true? What if we take that as a fundamental postulate and follow the consequences wherever they lead? What he found was that space and time are not independent things. They are woven together into a single fabric space-time, and that measurements of space and time are not absolute. They depend on the relative motion of the observer. 2 observers moving relative to each other will, when they compare notes, genuinely disagree about the length of an object, about the order in which events occurred, and about the amount of time that has passed between two events. These are not measurement errors. They are not illusions. They are real physical differences rooted in the geometry of spacetime itself. Here is where the most important misconception about Einstein tends to appear, and it is worth addressing directly because it shapes how people think about time near black holes. When people hear that time is relative, they often interpret this as meaning that time is somehow subjective, a matter of perception, that everyone experiences time differently the way everyone experiences colors differently, a quirk of individual consciousness rather than a feature of physical reality. This is not what Einstein meant at all. Time dilation. The slowing of time due to relative motion or gravity is objective, measurable, and universal. It does not depend on who is doing the experiencing. If two atomic clocks start synchronized, one stays stationary and one moves at high speed and then returns. The moving clock will show less elapsed time. Not because the clock is broken, not because the clock's mechanism was affected by the motion, but because for that clock, less time genuinely passed. Fewer seconds occurred. This has been measured, repeatedly, with extraordinary precision. In 1971, physicists Joseph Haffel and Richard Keating placed cesium atomic clocks on commercial airplanes flying around the world in both directions. When the clocks were returned and compared with identical clocks that had stayed on the ground, they showed exactly the differences that Einstein's equations predicted, accounting for both the velocity of the aircraft and the reduced gravitational influence at altitude. The differences were tiny, on the order of hundreds of nanoseconds, but they were real, and they matched the theory to within the margin of experimental error. The universe actually keeps different times in different places and at different speeds. Now special relativity deals with motion, with the way time and space behave when objects move relative to one another. But it was built on a simplification. It treated gravity as absent, as though the universe were flat and empty. Einstein knew this was not good enough. He spent the next 10 years from 1905 to 1915 trying to incorporate gravity into his framework. It was, by his own description, the most difficult intellectual work of his life. He later said that, compared to the effort required for general relativity, special relativity had been child's play. The core insight of general relativity is this: gravity is not a force transmitted between objects across space in the way Newton had imagined. Gravity is the curvature of space-time itself, caused by the presence of mass and energy. Where mass exists, space-time curves, and objects moving through curved space-time follow the straightest possible path. Through that curve, a path called a geodesic. What we perceive as the attractive pull of gravity is simply the natural motion of objects following the geometry of a curved space-time. This reframing has a consequence for time that goes far beyond what special relativity alone could describe. Not only does time pass differently for observers moving at different speeds, time also passes differently for observers at different positions in a gravitational field. The deeper you are in a gravitational well, the closer you are to a massive object, the more slowly time passes for you, relative to someone farther away. This is called gravitational time dilation, and it is not an approximation or a limiting case. It is a fundamental prediction of general relativity baked into the structure of the theory from the very beginning. Let us make this concrete because abstract principles only come alive through real examples. The surface of the Earth is deeper in Earth's gravitational well than the orbits where GPS satellites travel. This means that from the perspective of the satellites, clocks on the ground run very slightly slower, by approximately 45 microseconds per day. At the same time, the satellites are moving fast enough that their clocks also experience a different kind of time dilation due to their velocity, the kind described by special relativity. This effect runs in the opposite direction. Moving clocks tick slower, so the satellite clocks lose about 7 microseconds per day relative to ground clocks from velocity alone. Combining the two effects, GPS satellite clocks run fast by a net of about 38 microseconds per day relative to clocks on the ground. 38 microseconds sounds trivial, and it is trivial in the context of human experience. But GPS navigation relies on timing signals accurate to within fractions of a microsecond. If the relativistic corrections were not applied, if the satellite's clocks were allowed to drift, the accumulated error in position, calculations would reach roughly 11 kilometers per day. Every GPS system on Earth would become useless within a matter of hours. General relativity is not a theoretical curiosity. It is infrastructure. It is embedded in the technology that guides aircraft ships, emergency responders, and the delivery driver who brought something to your door. Einstein wrote his field equations in a small apartment without a laboratory. The equations now run quietly inside satellites, orbiting 20,000 kilometers above the ground, keeping the world navigated. There is something almost quietly astonishing about the timeline here that deserves a moment of attention. Einstein published General Relativity in November 1915. The first GPS satellite was launched in 1978, 63 years later. The full GPS constellation became operational in 1993. And today, billions of people use GPS every day without knowing that its accuracy depends on a correction factor derived from equations written by a man who had never seen a satellite, never imagined a smartphone, and who spent his most productive years working in a patent office because the academic world was not sure what to make of him. Ideas, it seems, do not always find their applications quickly, but they find them. Now, there is one more piece of Einstein's framework that we need before we can fully step up to the edge of a black hole and peer in. It is the question of what happens not just when space-time is curved moderately, as it is near Earth or near ordinary stars, but when it is curved to an extreme to the maximum that physics can describe. General relativity predicts that for sufficiently massive compact objects, the curvature of space-time near the object becomes so severe that the geodesics, those paths that particles and light naturally follow, all point inward. Not just some of them, all of them. There is no outward path. There is no trajectory that leads away. Every possible future for anything that crosses a certain boundary leads toward the center. That boundary is the event horizon, and inside it, something happens to the relationship between space and time that is not just quantitatively extreme, but qualitatively different, so different that the words before and after begin to lose their familiar meaning. What does it mean for time to have only one direction? What does it mean for the future to be a place rather than a when? Those questions are not rhetorical. They have precise mathematical answers within general relativity. And those answers are among the strangest, most beautiful, and most unsettling things that physics has ever produced. The event horizon is the threshold between the physics we know and the physics we are still trying to understand. It is the shore at the edge of everything familiar. And now that we understand the ground we are standing on, now that we know why Einstein's equations matter, why time curves, why gravity is geometry, we are ready to walk to that shore and look across it. Imagine you are standing on a beach at night. The water is dark. The waves come in slowly, quietly, one after another. You can walk into the water. You can wade out past your knees, past your waist. The current is gentle. Nothing feels particularly dangerous. But somewhere out there beyond what you can see, beyond what the darkness will reveal, there is a point past which the current runs faster than any swimmer can move. A point past which every stroke, every kick, every ounce of effort carries you not toward shore, but away from it. Not because the water is violent, not because anything has changed in how the water feels, but because the geometry of the current has shifted quietly and completely against you. You would not know you had crossed that point until you tried to turn back, and by then, it would be too late. This is the event horizon, not a wall, not a surface you could press your hand against, not a visible line drawn in the dark, just a threshold defined entirely by mathematics, by the curvature of space-time, beyond which every possible path through the future leads in one direction only, inward. The concept of a boundary from which light cannot escape is older than Einstein. It is in fact older than the theory of light itself, as we understand it today. In 1783, a British clergyman and amateur scientist named John Michell sat down with Newton's laws of gravity and asked a simple question. Newton had shown that any projectile launched from a planet's surface needs to reach a certain speed to escape that planet's gravity entirely. For Earth, that speed is approximately 2 kilometers per second. Fire something slower than that, and it falls back. Fire it faster, and it escapes into space. Michel asked, what if a star were so massive, so dense, that the escape velocity from its surface exceeded the speed of light? At the time, there was a theory that light consisted of tiny particles, corpuscles, that obeyed the same laws of motion as everything else. If that were true, then a sufficiently massive and compact star would be able to trap its own light. The corpuscles would rise from the surface, slow down, under the pull of gravity, stop, and fall back. From the outside, such a star would be invisible, completely dark, present only through its gravitational influence on nearby objects. Michel called these objects dark stars. He wrote up the idea and sent it to the Royal Society of London. It was published. It was noted. And then for over a century, it was almost entirely forgotten, because the particle theory of light fell out of favor, replaced by the wave theory. And waves, it seemed, could not be trapped by gravity the way particles could. The idea of dark stars went quiet. It took Einstein's General Relativity and Schwarzschild's solution in the trenches of World War I to resurrect the concept on a completely different and far more rigorous foundation. And what emerged was something subtler and stranger than Michel's dark star. Not just a place where light is too slow to escape, a place where the very structure of spacetime makes escape geometrically impossible. To understand why the event horizon is so strange, we need to think carefully about what it means for light to be unable to escape. In ordinary space, you can point a flashlight in any direction you choose. You can aim it up, down, left, right, forward, backward. Light travels in straight lines through flat space-time, and if nothing is in its way, it will travel outward indefinitely. Near a massive object, space-time curves. The paths that light follows, those geodesics, the straightest possible lines through curved space-time, begin to bend. Near Earth, the bending is tiny. Near a neutron star, it becomes significant. Light passing close to a neutron star is visibly deflected. This was confirmed during the solar eclipse of 1919, when Arthur Eddington led an expedition to observe stars near the edge of the sun's disk, and found they were displaced from their expected positions by exactly the amount general relativity predicted. That observation made Einstein world famous overnight. But near a black hole, as you approach the event horizon, the bending of light paths becomes more and more extreme. At a certain distance, called the photon sphere, located at 1.5 times the Schwarzschild radius, light can actually orbit the black hole. A photon moving in exactly the right direction, at exactly the right distance, will travel in a perfect circle, going around and around the black hole, indefinitely, never escaping, never falling in. This is not a metaphor. Physicists believe that if you were positioned at the photon sphere and looked in precisely the right direction, you would see the back of your own head, light that had traveled all the way around the black hole and returned to your eyes. And as you move closer, still past the photon sphere toward the event horizon itself, the situation becomes more extreme. The outward-pointing light cones, the geometric structures that represent all possible future directions for light, begin to tilt inward. More and more of the future is pointing toward the center of the black hole. And at the event horizon, the tipping is complete. Every future direction, even the one that was pointing directly away from the black hole, now points inward. There is no outward anymore. The word itself has lost its meaning. Now here is the paradox that sits at the heart of this. And it is one of the most genuinely mind-bending aspects of general relativity. For someone watching from far away, let us call her the distant observer. What does she see when she watches someone fall toward the event horizon? She sees something extraordinary. She sees the falling person slow down. Not because the person is hesitating, not because anything is stopping them, But because the light carrying images of the falling person is climbing out of increasingly curved space-time, and in doing so, it becomes progressively more stretched, more redshifted, more time dilated. From the distant observer's perspective, the falling person appears to slow and slow and slow. The person's movements become more languid. The signals take longer and longer to arrive. The image grows dimmer and redder. And as the falling person approaches the event horizon, asymptotically never quite reaching it in the distant observer's frame of reference, they appear to freeze, to hover, to become a ghostly red-shifted silhouette, suspended forever at the edge of the unknown. They never, from the distant observer's perspective, actually cross the horizon. They appear to hang there for an infinite amount of time, growing fainter, stretching toward red, and then infrared, until the signal drops below detectable thresholds and they simply vanish. But now, consider the falling person's own experience. From their perspective, from inside the fall in their own reference frame, nothing dramatic happens at the event horizon. There is no wall. There is no flash of light. There is no sensation of crossing a threshold. If the black hole is large enough, the tidal forces at the horizon are gentle enough that the person might not feel anything unusual at all as they pass through. They cross the event horizon without ceremony, and yet they have just crossed the most absolute boundary in the known universe. From the outside, they appear frozen forever. From the inside, they are still falling. Both of these things are simultaneously genuinely true. They are different descriptions of the same events from different reference frames. And in a universe where space-time is curved, neither frame is wrong. Both are legitimate. Both are real. This is perhaps the most profound illustration of what Einstein meant when he said that time is relative. Not relative as in approximate. Relative as in fundamentally dependent on where you are in the geometry of the universe. Have you ever watched someone walk away from you, growing smaller in the distance until they disappeared around a corner, and knew that, from their perspective, they simply kept walking forward, unaware of how they looked to you? What happens at the event horizon is something like that, but taken to an absolute extreme. The corner they turned is the edge of everything knowable. There is a term physicists use for the region of space-time that the distant observer can never receive information from. It is called the causal future of the event horizon, and it includes everything that happens beyond that boundary. This is not merely a practical limitation the way that a mountain range limits what you can see from a valley. It is a fundamental feature of the space-time geometry. The information about what happens beyond the event horizon cannot, in principle, be transmitted to the outside. Not because the technology is not good enough, not because the signal is too weak, but because the causal structure of space-time beyond the horizon simply does not connect to the outside anymore. What happens inside a black hole is, in the most literal sense, none of the outside universe's business. This creates a question that has haunted physicists for half a century, and which we will return to in detail later in our journey, if information about what falls into a black hole can never come out. What happens to it? Is it destroyed? Is it hidden? Or is it somehow, in some form we do not yet understand, preserved? But we are not yet ready for that question. There is something else we need to understand first. When Carl Schwarzschild first derived his solution in 1915, the mathematics contained what appeared to be a catastrophic breakdown at 2 points. The first was at the Schwarzschild radius, what we now call the event horizon. The second was at the center, what we now call the singularity. At the Schwarzschild radius, certain quantities in the original form of the equations appeared to blow up to become infinite. And for many years, physicists debated whether this meant something genuinely pathological was happening at that radius, or whether it was merely an artifact of the coordinate system being used the mathematical language rather than the physics itself behaving badly. The resolution, which came gradually through the work of multiple physicists over several decades, was that the Schwarzschild radius singularity is indeed a coordinate artifact. If you choose a different mathematical coordinate system, one better suited to describing what happens across the horizon, the apparent catastrophe disappears. The crossing of the event horizon for the infalling observer is smooth and uneventful, exactly as the physics suggests it should be. The singularity at the center is a different matter entirely. That one does not go away when you change coordinates. It appears to be a genuine feature of the geometry, a place where the curvature of spacetime becomes infinite, where the equations break down in a way that no change of perspective can repair. We will get there. But first, we have to fall a little further. There is one more aspect of the event horizon that is worth sitting with before we move deeper, because it is something that surprises almost everyone when they first encounter it. The event horizon of a black hole is not a small thing. For stellar mass black holes, the kind formed from the collapse of individual massive stars, the event horizon might be a few kilometers across, comparable to a city, small by astronomical standards. But at the center of our own galaxy, the Milky Way, there sits a black hole called Sagittarius A star. It has a mass of approximately 4 million suns, and its event horizon, the Schwarzschild radius of that mass, is roughly 24 million kilometers across. For comparison, the distance from Earth to the Moon is about 384,000 kilometers. The event horizon of Sagittarius A star is about 60 times the Earth-Moon distance in diameter. It would swallow Mercury's orbit with room to spare. And Sagittarius A star is not even particularly large as supermassive black holes go. The black hole at the center of the galaxy, Messier 87, the one that was photographed directly for the first time in 2019, producing that iconic image of a glowing ring around a dark shadow, has a mass of approximately 6.5 billion suns. Its event horizon is larger than our entire solar system. An event horizon larger than the solar system. A region of no return that a spacecraft could wander into, without the passengers feeling a single unusual thing, crossing a boundary that quietly and completely severs them from the entire rest of the universe, while from the outside they appear to hang suspended in time forever. The universe contains structures of an almost incomprehensible scale of strangeness, and the strangeness does not stop at the horizon, because inside that boundary, something happens to time that goes beyond slowing, beyond dilation, beyond anything we have described so far. Inside the event horizon, the very roles of space and time, as we experience them, appear to swap. What was the dimension of time becomes a dimension of space pointing inward, and what was the spatial direction pointing toward the center becomes, in the most literal mathematical sense, the future. Inside a black hole falling toward the center is not moving through space, it is moving through time. The singularity at the center is not a place you travel to. It is a moment you fall toward, and understanding what that means, truly understanding it, requires us to go somewhere even stranger than the edge. It requires us to follow the path of something that has already crossed over, already left the shore behind, and is drifting now through a universe that has only one direction left. Deeper can influence what happens outside. The information cannot get out. The geometry forbids it. Both horns of this dilemma are deeply uncomfortable, and for 3 decades the greatest minds in theoretical physics argued passionately about which horn to accept. Hawking himself, for most of his career, believed that information was lost. He argued that black holes represent a genuine exception to quantum mechanical unitarity, that the universe at this extreme breaks its own rules. This was not a casual position. Hawking was one of the most rigorous thinkers in physics. He believed the mathematics forced this conclusion. On the other side stood Leonard Susskind, a physicist at Stanford, and Gerard de Hooft, a Nobel laureate from the Netherlands. They argued with equal rigor that information could not be lost, that whatever quantum gravity turned out to be, it had to preserve information. Hawking was wrong. The universe does not cheat. Susskind has written about the intensity of this disagreement with characteristic directness. He and Hawking debated it at conferences and papers in private conversations. For years, the field was split. Brilliant people looked at the same mathematics and drew opposite conclusions. The confrontation was not merely academic, It was in Susskind's description a battle for the soul of physics. If Hawking was right, quantum mechanics was not the fundamental law it appeared to be. If Susskind was right, then our picture of what happens inside a black hole based on general relativity had to be revised in some dramatic and as yet unknown way. The resolution, or at least the beginning of a resolution, came from an unexpected direction. In 1997, a young Argentine-American physicist named Juan Maldacena published a paper that would become one of the most cited in the history of theoretical physics. It described a mathematical equivalence, a duality between a theory of gravity in a certain type of curved spacetime and a quantum field theory living on the boundary of that spacetime with no gravity at all. This became known as the ADS/CFT correspondence, and its implications for the information paradox were enormous. If Maldacena's duality is correct, and the evidence that it is has accumulated steadily over more than 2 decades, then the physics of a black hole in the gravity theory is exactly equivalent to a perfectly well-behaved quantum theory on the boundary, and quantum theories on boundaries are unitary. They conserve information by construction. Therefore, if the duality holds, information must be conserved in black hole physics as well. The black hole's interior, the evaporation, the Hawking radiation, all of it must somehow be consistent with unitarity. Information is not lost. It is encoded, scrambled, distributed, but preserved. In 2004, at a conference in Dublin, Stephen Hawking publicly conceded. He acknowledged that he had been wrong about information loss, that black holes do not destroy information, and that the information eventually escapes in subtle correlations within the Hawking radiation. He paid off a bet he had made years earlier with the physicist John Preskill, presenting him with a baseball encyclopedia, a repository of information, as the forfeit. It was a remarkable moment. One of the most celebrated scientists of the 20th century, standing before his peers saying I was wrong. The universe keeps its records. But conceding that information is preserved is not the same as understanding how. And the how is where the story becomes stranger still. If information escapes in the Hawking radiation, it must somehow get out despite the causal barrier of the event horizon. The geometry says nothing from inside can affect outside. So either the geometry is wrong, which general relativity strongly resists, or the information never truly went inside in the first place. This second possibility has given rise to one of the most radical ideas in contemporary physics, the holographic principle. The holographic principle, developed from work by 't Hooft Susskind and others in the 1990s, proposes that all the information describing the interior of a black hole, everything that has ever fallen in, is actually encoded on the event horizon itself, not inside, on the surface. Like a hologram, which encodes a 3-dimensional image on a 2-dimensional surface. The black hole encodes its 3-dimensional interior information on its 2-dimensional boundary. From this perspective, nothing is ever truly inside the black hole in a way that severs it from the outside. The horizon is not a one-way door through which information disappears. It is a surface on which information is written in a form that is scrambled beyond any practical decoding, but that is in principle there. The interior that infalling observers experience the space, the time, the continuation of their fall, may be in some deep sense a projection. A description that is valid for the observer inside, but which has a completely different and equally valid description from the outside one in which the information never crossed the horizon at all. Here is the part that is almost too strange to sit with calmly. These two descriptions, the infalling observer, experiencing a normal crossing of the horizon and continuing to fall, and the outside observer seeing information encoded on the horizon surface, are not contradictions. They are complementary. No single observer can access both descriptions simultaneously. The infalling observer, once inside, cannot communicate with the outside to compare notes. The outside observer can never directly verify what the infalling observer experiences. This principle that two radically different descriptions can both be valid applied to the same physical situation as long as no single observer can access both, is called black hole complementarity. It was developed primarily by Susskind and his colleagues in the early 1990s, and it represents one of the most philosophically challenging ideas in modern physics. The universe, it seems, permits different realities for different observers, as long as those realities never directly contradict each other in a way that can be tested. Does time remember everything? The best answer physics can currently give is yes. But in a language so scrambled distributed across the quantum correlations of radiation, emitted over billions of years, encoded on surfaces, we cannot directly read expressed in mathematical dualities. We are still learning to translate that remembering and forgetting look from the outside, almost indistinguishable. What endures through all of this, through the paradox, through the concession, through the holographic principle and complementarity and the duality that Maldacena found, is a sense that the universe has a deep commitment to honesty, that it does not quietly erase. That even the most extreme process known to physics, even the singularity and the event horizon, and the long, slow evaporation of a black hole over time scales that dwarf the current age of the universe, does not constitute an exception to the fundamental rule that what exists existed. Time in this sense may be the universe's memory, the way that cause and effect are linked irreversibly and completely from the beginning to the end of everything. And if that is true, if the universe truly keeps every record, even the ones swallowed by black holes, then what does it mean for the nature of time itself? Not just near a black hole, not just in extreme conditions, but here in the ordinary flow of moments that carries us through every day. What does it mean that the present moment, this one, the one you are resting in right now, is in principle, written into the structure of the universe permanently, that it cannot be unmade? That question is not physics, or rather, it is physics becoming something else, something that reaches past equations and into the quiet territory where science and wonder share a border. And that territory is exactly where we are going in the final part of this journey. We have traveled a long way tonight. We began with a clock in Bern, Switzerland, and a young man who could not stop staring at it. We watched stars die in fire and silence. We stood at the edge of the event horizon and looked in. We fell through tidal forces that could stretch matter into threads of atoms. We orbited a black hole where 1 hour equaled 7 years of someone else's life. We descended toward a singularity where the equations of physics quietly confessed they had reached their limit. And we sat with the extraordinary idea that even information, even the record of what has existed, may be the one thing the universe refuses to erase. That is a long journey for a quiet night. And now, we have arrived at the last question. Not the hardest one scientifically, but perhaps the one that sits closest to the reason any of us finds ourselves drawn to these stories in the first place. What does all of this mean? Not for physics, not for the equations, but for us. For the experience of being alive in a universe that contains black holes. For the way we understand the time that we are right now moving through. Let us start with something concrete, because concrete things are the best bridges to the abstract. In 2019, the Event Horizon Telescope collaboration, a network of radio telescopes spread across the entire surface of the Earth, linked together to function as a single instrument the size of the planet, published the first direct image of a black hole's shadow. The black hole was Messier 87 star, 6.5 billion solar masses, a distance of 55 million light-years from Earth. And the image, that glowing orange ring around a dark central void that appeared on the front page of newspapers and websites across the world, was not an artist's rendering. It was not a simulation. It was a photograph. Light that had traveled 55 million years to reach us, bent by the light from stars, from galaxies, from all the history that continues to unfold outside, can still reach them, because light can fall inward just as easily as matter can. But as the observer continues to fall, the angle from which outside light can reach them narrows. The window onto the exterior universe contracts. Eventually, As the singularity approaches the entire history of the exterior universe, everything that will ever happen outside the black hole, between the moment of crossing and the infinite future, appears to be compressed and blue shifted into a narrowing cone of light arriving from directly ahead. The outside universe does not end when you cross the horizon. From inside, it keeps going. You can still, in principle, see it, but you can no longer reach it, and it cannot reach back. One more aspect of spaghettification deserves attention, because it is relevant to something scientists actually observe and measure. When matter falls toward a black hole, not a lone and falling observer in a thought experiment, but real gas and dust and torn apart stars, it does not typically fall straight in. It swirls. It forms a disk called an accretion disk of material spiraling inward. The tidal forces in this disk are immense. They heat the material through friction and compression to temperatures of millions of degrees. The disk glows ferociously, often outshining the entire galaxy surrounding it across every wavelength, from radio waves to X-rays and beyond. These are what we call quasars and active galactic nuclei, some of the brightest objects in the observable universe, powered entirely by the gravitational energy released as matter spirals toward a black hole and is spaghettified, heated, and ultimately consumed. The tidal forces that would stretch a human into a thread of atoms are at galactic scales the engine of some of the most luminous phenomena in the cosmos. The same physics that kills at human scales illuminates at cosmic ones. We have now watched stars die, watched the event horizon form, watched light bend and freeze and hover at the edge of the infinite. We have felt, at least in imagination, the pull of tidal forces and the strange gradient of time flowing differently at our head than at our feet. But there is a question we have been circling, one that has been waiting patiently since the very beginning of this journey. If you are the infalling observer, if you have crossed the horizon, if spaghettification has not yet taken you, if you are still drifting inward through the interior of a supermassive black hole in those final moments, before the singularity, what does time look like to you? Not from outside, not from the perspective of someone watching you fade and freeze at the horizon, but from inside, from the place no equation can fully describe and no message can ever leave. And for that, we need to talk about something that is not just 1 hour equaling 7 years. We need to talk about the place where time dilation reaches its logical and physical extreme, where the clock does not just slow, where the clock approaches something that from the outside looks indistinguishable from stopped, where 1 hour to you might mean the rise and fall of entire civilizations out there in the universe you left behind. That conversation is the one we turn to now. In 2014, a film appeared in cinemas that did something almost no science fiction film had attempted before. It tried to be accurate, not in the way that science fiction is usually accurate, meaning visually plausible, meaning the spaceships looked convincing, and the planet seemed real, but accurate in the deeper sense. The physics was worked out by an actual physicist. The mathematics was genuine, and the central premise was not invented for dramatic effect. It was taken directly from General Relativity. The film was Interstellar. And the moment that stunned audiences, most the moment that generated more genuine conversation about physics than perhaps any scene in cinematic history, was not an explosion, not a chase, not a revelation about a character. It was a scene in which a team of astronauts landed on a planet orbiting a supermassive black hole. They spent a little over an hour on the surface, and when they returned to their ship, they found that their colleague who had waited in orbit had aged 23 years. 23 years. While they experienced 1 hour, audiences sat in silence. Some laughed because the mind reaches for humor when it encounters something it genuinely cannot process. Some cried without entirely knowing why. And the most important thing about that scene is this: it was not fiction. Gravitational time, dilation. The slowing of time in a strong gravitational field is a prediction of general relativity that has been confirmed experimentally at every scale we can measure. We have established this in earlier chapters. But near a black hole, the effect does not merely scale upward in a linear way. It accelerates, it compounds, and as an object approaches the event horizon, it approaches a limit that is not just quantitatively extreme, but qualitatively unlike anything in ordinary experience. To understand why we need to think carefully about what the time dilation formula actually says. In the weak field approximation, meaning far from a black hole in regions where the gravitational field is relatively gentle, the amount by which time slows down at a given location depends on how deep you are in the gravitational potential. A clock on the surface of the Earth runs slower than one in orbit. A clock on the surface of a neutron star would run dramatically slower. These differences are real and measurable and follow a formula that Einstein derived directly from his field equations. But as you approach a Schwarzschild black hole, a non-rotating black hole of the type we have been primarily discussing, the formula predicts something startling. The time dilation factor does not approach some large finite number. As you approach the event horizon, it approaches infinity. From the perspective of a distant observer, a clock falling toward the event horizon slows down without limit. It never reaches zero time, does not stop for the infalling observer from their own perspective. But for every second that ticks on the infalling clock, an observer far away sees an ever-increasing amount of their own time pass. And at the horizon itself, the ratio becomes infinite. 1 second of infalling time corresponds in the distant observer's frame to an eternity. This is what it means for the infalling observer to appear frozen at the horizon forever from the outside. It is not illusion. It is the literal content of the mathematics. Now, let us put real numbers to this, because the abstract and the concrete illuminate each other. The planet in Interstellar called Miller's Planet in the film orbits a black hole named Gargantua. For the time dilation depicted to be accurate, the planet would need to be orbiting extraordinarily close to the event horizon of an extraordinarily massive black hole, spinning at nearly the maximum possible rate. Kip Thorne, the Caltech physicist who served as the film's scientific executive producer, worked out that for 1 hour on the surface to correspond to 7 years in orbit above the planet would need to be within roughly 1/1,000,000% of the innermost stable orbit around a maximally spinning black hole of enormous mass. This is, to put it gently, an extreme set of conditions. The planet would be bathed in radiation from the accretion disk. Its orbital mechanics would be fantastically complex. The tidal forces, while survivable near a large enough black hole as we discussed, would still be significant. In the film, those giant waves on the surface, some of the most visually striking imagery in the movie, are the tidal expression of the black hole's enormous gravitational gradient. They are not mere weather. They are the black hole reaching out and physically reshaping the ocean through differential gravity. But the time dilation itself, 1 hour equaling 7 years, is not invented. It is within the range of what the equations permit given the right conditions. Think about what that means in human terms. You descend to the surface of a world that orbits a black hole. You spend an hour there. You return. And everyone you knew, every friend, every colleague, every child who waved goodbye when your mission launched has lived 7 years of their life while you lived 1 hour of yours. They have celebrated 7 birthdays. They have watched 7 winners come and go. They have had 7 years of ordinary Tuesdays and extraordinary moments and small, unremarkable evenings. And you have had 1 hour. Your watch and their watch both worked perfectly. Neither was broken, neither was tampered with. They simply measured different amounts of time because they existed in different regions of the geometry of space-time. But here is a question worth sitting with, because it is one that gets to the heart of what time dilation actually means for our experience of reality. If you were on that surface, if you were the one experiencing the hour, would you know that time was passing differently for you? The answer, which surprises people every time, is no. Your heartbeat would feel normal. Your thoughts would flow at their ordinary pace. Your coffee, if you had brought coffee to the surface of an alien world orbiting a black hole, and perhaps you would, because some habits persist, even into the extraordinary, would cool at what felt like the ordinary rate. Every subjective aspect of your experience would be exactly as it always was. The hour would feel like an hour. There is no sensation of living in slow motion. There is no awareness of the universe rushing ahead outside. The physics does not announce itself. It simply occurs silently in the geometry, while your body and mind go about their entirely normal business of being alive. And this is perhaps the most profound lesson that gravitational time dilation teaches: the universe does not care what our experience tells us. Our intuition says that if time were truly passing differently, we would feel it. Our intuition is wrong. The universe operates according to geometry, not sensation. Space-time curves according to mass and energy, and clocks tick according to where they are in that curvature. And the living beings carrying those clocks feel nothing unusual at all. We are, in a sense, always at the mercy of a geometry we cannot directly perceive. There is a real-world observation that brings this home in a way that no thought experiment quite can. At the center of our own Milky Way galaxy, roughly 26,000 light-years from Earth, sits Sagittarius A star, the 4 million solar mass black hole we have mentioned before. In 2002, a team of astronomers led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics began tracking the orbits of individual stars in the dense cluster surrounding Sagittarius A star. One of those stars, designated S2, has an orbital period of roughly 16 years. Its orbit carries it on a highly elliptical path that brings it at closest approach to within about 120 astronomical units of the black hole. That is roughly 120 times the distance from Earth to the Sun, an enormous distance by human standards, but extraordinarily close for a star orbiting a supermassive black hole. In 2018, as S2 approached its closest point, called periapsis, the team detected something. The light from S2 was redshifted, not just by the Doppler effect of motion, but by an additional component consistent with gravitational time dilation. The light climbing out of the gravitational well of Sagittarius A star was stretch-shifted toward longer wavelengths, carrying the imprint of time, passing more slowly in that region of space. This was the first direct detection of gravitational redshift near a supermassive black hole. The star S2, at its closest approach, was experiencing time running measurably more slowly than it does out here where we are. The black hole at the center of our galaxy is warping time as we watch, not as metaphor, as measurement. Now, let us think about the cumulative effect of this over cosmic timescales, because this is where the implications become genuinely staggering. Our galaxy is approximately 13.6 billion years old. Sagittarius A star has been sitting at its center for most of that time, a gravitational anchor around which hundreds of billions of stars orbit in a slow, majestic pinwheel. Stars and gas clouds and dust that have orbited close to Sagittarius A star over those billions of years have aged differently than stars at the outer edges of the galaxy. The cumulative time dilation experienced by objects that have spent billions of years in a stronger gravitational field is not trivial. Over geological timescales, the differences add up. In principle, though, not practically given the distances and other complexities involved. If you had placed identical atomic clocks on Earth and on a planet orbiting much closer to Sagittarius A star at the galaxy's formation, and if those clocks had survived 13 billion years, they would show different readings today. The clock near the black hole would be behind. By how much depends on exactly how close it was, but the answer would be measurable real and encoded in the geometry that has governed both clocks since the beginning. The universe is not the same age everywhere. The oldest things in regions of strongest gravity are, in a precise technical sense, younger than equally old things in weaker gravitational fields. There is one more aspect of extreme time dilation that deserves to be named before we move deeper, because it connects the abstract physics to something with a peculiar and affecting beauty. When we say that a clock near the event horizon runs almost infinitely slowly relative to a distant observer, we are also saying something about information, about light, about what can be known. Light from an object near the event horizon takes longer and longer to reach us, as we have discussed. But it is not just that the signal is delayed. The signal itself is stretched. Each wavelength of light emitted near the horizon is elongated as it climbs the gravitational gradient, shifted toward lower frequencies, toward the red end of the spectrum, and then beyond it into infrared, into microwave, and finally into radio waves too faint to detect. This stretching of light is called gravitational redshift, and it is the direct observational signature of time dilation. When we see light from near a black hole shifted toward red, we are watching the photons carry the news of a slower time. We are seeing in the color of light the imprint of spacetime's geometry. Every photon that reaches us from a region of strong gravity has, in a sense, aged differently than it would have if it had traveled through flat, empty space. It has been stretched. It has been slowed. It carries within its wavelength the record of the curved space-time it passed through. Light, it turns out, is a messenger not just about the objects that emit it, but about the geometry of the space it traveled through to reach us. And if that is true for light in regions, we can observe if even the photons carry the signature of time, dilation in their very wavelengths. What does this tell us about what happens inside the horizon, where no photon can escape at all? What happens to time when there is no light left to carry the news? When the geometry becomes so extreme that even the concept of a signal reaching the outside becomes meaningless? To answer that, we have to go somewhere that no equation can fully describe, somewhere that sits at the edge of everything human mathematics has built, where the numbers reach toward infinity, and physics as we know it quietly confesses that it does not know what happens next. We have to go to the singularity. There is a moment in every great map where the lines simply stop. In medieval cartography, the edges of the known world were sometimes marked with a phrase in Latin, hic sunt dracones, here be dragons. Not because the map makers believed in dragons necessarily, but because they had no information about what lay beyond. The map had reached its limit, the territory continued, but the tools for describing it had run out. Physics has its own version of that boundary. It is not at the edge of a flat Earth. It is not at the border of a known continent. It is inside a black hole at the very center, at a point that every infalling particle and every ray of light is ultimately drawn toward, at a point where the curvature of space-time, according to General Relativity, becomes not merely extreme, but infinite. It is called the singularity. And beyond it, or rather at it, the dragons begin. Let us be precise about what it means for a mathematical equation to produce an infinite answer, because this matters more than it might seem. In physics, infinity is not a destination. It is a diagnosis. When a physical theory produces an infinite value for a measurable quantity, it is telling you not that something in the universe is literally infinite, but that the theory itself has reached the edge of its own validity. The equations are breaking down. The model is no longer an adequate description of reality at that scale or in that regime. We have seen this before in the history of physics. Classical electromagnetism, when applied to a single point, electron predicts that the electric field at the electron's surface is infinite, which would imply the electron has infinite energy. This breakdown of classical theory at small scales was one of the motivations for developing quantum mechanics, which resolved the problem by changing the foundational picture. Similarly, the singularity at the center of a black hole is not a place where the universe itself becomes infinite. It is a place where general relativity, which has been extraordinarily accurate in every context, we have tested it, exceeds its own domain of applicability. It tells us that something we do not yet understand is happening, something that requires a theory we do not yet have. That missing theory is what physicists call quantum gravity, a framework that would unify general relativity with quantum mechanics, describing space-time itself at the smallest scales where both theories become relevant simultaneously. We do not have that theory yet. Several candidates have been proposed: string theory, loop quantum gravity, causal dynamical triangulations, Each captures something, each struggles with something else. None has been confirmed experimentally. None has produced a complete and universally accepted resolution to what happens at the singularity. So, when we ask what happens to time at the center of a black hole, we are asking a question that current physics cannot fully answer. We can describe everything up to a certain point, and then the map ends. But let us describe what we do know, because even approaching the edge is extraordinary. Inside the event horizon, as we touched on in Part 4, something deeply strange happens to the roles of space and time. In ordinary space-time, outside any black hole, space and time have different characters. You can move freely through space, forward, backward, left, right, up, down, but time flows in only one direction. You cannot choose to go backward in time the way you can choose to turn around in space. Time is a directed dimension, pointing always toward the future. Inside the event horizon, this distinction breaks down, and not in a vague or poetic sense, but in a precise mathematical one. In the Schwarzschild solution for a non-rotating black hole, once you have crossed the event horizon, the radial coordinate, the one pointing toward the center of the black hole, takes on the mathematical character of a time coordinate. It becomes a directed dimension, pointing toward a future that is the singularity. And the time coordinate of the outside world, the coordinate that out there was always pointing forward, takes on the character of a spatial coordinate inside. What this means physically is that the singularity is not a place you are falling toward. It is a moment you are approaching. The center of the black hole is not a location in space that exists at some particular time. It is a moment in time that everything inside the horizon is inevitably moving toward the way all of us outside are inevitably moving toward the future. You cannot avoid the singularity inside a black hole for the same reason you cannot avoid next Tuesday. It is not in front of you, it is ahead of you in time. Roger Penrose, the British mathematical physicist who shared the 2020 Nobel Prize in Physics, proved something extraordinary about singularities in 1965. Working with a series of mathematical theorems that are among the most elegant in 20th century physics, Penrose demonstrated that singularities are not a peculiarity of perfectly symmetric solutions to Einstein's equations. They are not artifacts of the idealized, perfectly spherical black holes that Schwarzschild had considered. They are inevitable. Penrose's singularity theorems showed that once a sufficient amount of matter collapses into a small enough region, once an event horizon forms, general relativity guarantees the existence of incomplete geodesics, paths through spacetime that simply end. They do not reach a boundary and bounce back. They do not continue outside the region. They terminate. The world lines of particles and photons, which in ordinary spacetime continue indefinitely into the future, simply stop having a future. Stephen Hawking then extended Penrose's theorems in the other direction, showing that the Big Bang itself, the beginning of the observable universe, contains a singularity of the same mathematical type. The beginning of time in general relativity is as singular as the interior of a black hole. This is a remarkable symmetry. The universe began with a singularity, and inside every black hole, particles and light end at one. The theory that describes the large-scale structure of the cosmos, applied consistently to its own implications, produces these endpoints, these places where the description simply stops. Now let us ask the question that is hardest to answer, but most important to sit with: what does time actually do at the singularity? For the infalling observer, the person or object that has crossed the horizon and is being drawn toward the center, proper time continues ticking normally all the way in. From their own perspective, they are moving through time at the same rate they always have. Their clock ticks. Their thoughts occur in sequence. Cause still precedes effect in their local experience. But the duration of that experience inside the horizon is finite, remarkably precisely calculably finite. For a non-rotating Schwarzschild black hole, the time between crossing the event horizon and reaching the singularity measured in the proper time of the infalling observer is predictable. It depends on the mass of the black hole. For a stellar mass black hole of perhaps 10 solar masses, The journey from horizon to singularity takes roughly 10 to 50 microseconds, less time than it takes to blink. The violence of the tidal forces we discussed in Part 5 would, for such a small black hole, have already destroyed any ordinary matter long before it reached the singularity. But the geometry says the end would come impossibly fast. For a supermassive black hole of 1 billion solar masses, the journey from horizon to singularity in proper time might last on the order of hours or even days, long enough to conduct experiments, long enough to observe, long enough to wonder in a way that stellar mass black holes do not permit. But finite, always finite, the singularity arrives. And in general relativity, it is not merely a dangerous place. It is the end of the geodesic. The world line stops. There is no after. There is no further future for that particular path through space-time. Here is perhaps the most haunting consequence of this, and one that is rarely discussed in popular accounts. When a particle's world line ends at the singularity, it is not like the particle being destroyed in the way we normally think of destruction, converted into radiation, broken into smaller pieces, dispersed into the environment. In those ordinary forms of destruction, information is conserved. The constituent parts continue to exist. The universe still contains a record of what the particle was. At the singularity, the world line itself ends. There is no further space-time for the particle to exist in. It is not broken apart. It is not converted. The space-time that would have been its future simply does not exist. This is what makes the singularity genuinely different from anything else in physics. Not the violence, not the density, not the temperature which rises without limit as the singularity approaches, but the termination, the absence of any further description, the map that has not just reached its edge but has gone blank. What happens to the information that was encoded in the particle? This is where the singularity connects to one of the deepest unresolved puzzles in all of physics, a puzzle that we will explore in full when we turn to the information paradox. But for now, it is enough to sit with the strangeness that physics describes a place inside every black hole where a future simply ceases to exist for anything that reaches it. There is a school of thought among physicists that the singularity, while real as a mathematical object within general relativity, does not correspond to any physical reality in the universe. This view holds that whatever quantum gravity turns out to be, whatever the correct theory is, that reconciles general relativity with quantum mechanics, it will replace the singularity with something finite. Loop quantum gravity, for instance, suggests that space-time has a minimum size, a quantum of geometry, below which the concept of distance loses meaning. In this picture, the collapse does not continue to infinite density, but reaches some maximum density, and may in some formulations bounce, creating not an endpoint, but a transition to a new region of space-time that is disconnected from ours, a region that has been called a baby universe. String theory offers its own suggestions. Some formulations predict that the singularity is replaced by a tangle of strings and higher dimensional objects, whose behavior is governed by the full stringy physics rather than by the classical geometry of general relativity. None of these proposals has been confirmed. None has made predictions that can yet be tested. But almost every physicist working on quantum gravity believes that the classical singularity is a signal, not a truth, a wound in the theory that the next theory will heal. What the next theory will say about time at the center of a black hole, whether time continues in some form, whether it transforms into something else, whether it simply has no meaning, there nobody knows. This is one of the genuinely open questions at the frontier of human knowledge. Not open in the sense that different people have different opinions. Open in the sense that the answer has not yet been found. Do you find something strangely freeing in that? That here in the 21st century, with all our instruments and equations and satellites and detectors, there are still places in the universe, real physical places predicted by our best theories, about which we must honestly say, we do not know what happens there. Science is not a completed picture. It is a living, unfinished thing, still reaching toward the edges of its own maps, still marking places where the dragons begin. And those edges, those open questions are not embarrassments. They are invitations. Every singularity in the history of physics, every place where a theory broke down, has eventually led to a deeper, richer, more beautiful understanding of reality. The singularity at the center of a black hole may be the most profound such invitation that the universe has ever offered. And here is what makes that invitation even more remarkable. The black hole does not simply swallow information and fall silent. It speaks. Quietly, almost inaudibly, but it speaks. Stephen Hawking discovered in 1974 that black holes emit radiation, that they slowly over immense time scales lose mass and shrink and eventually perhaps vanish entirely, which raises a question that kept Hawking and his colleagues arguing for 30 years, a question about whether the universe is fundamentally honest, whether everything that falls in must in some form come back out. That question has a name, the information paradox, and it is where our journey goes next. Imagine you have a library, not a digital library, not a database somewhere on a server, but a real physical library. Shelves of books, hundreds of thousands of them, filling room after room, every volume containing the accumulated knowledge and stories and records of human civilization. Every birth certificate ever written, every love letter ever sent, every scientific paper, every recipe, every piece of music ever transcribed onto a page. Now, imagine that library catches fire. It burns completely. Nothing survives. Every page is reduced to smoke and ash and heat dispersed into the atmosphere. Is the information gone? The intuitive answer is yes. Obviously, yes. The library is destroyed. The knowledge is lost. There is no recovering it. But here is the thing that physics insists upon, quietly and firmly: the information is not gone. Not truly. The smoke carries the chemical signatures of what burned. The pattern of heat dispersed into the atmosphere encodes at the level of individual molecules the precise arrangement of ink on paper that preceded it. The information has been scrambled, transformed, made practically inaccessible. But in principle, if you could track every molecule, every photon, every quantum of energy that left that burning library, you could reconstruct everything that was lost. This is not a philosophical claim. It is a consequence of the fundamental laws of quantum mechanics, which state that the evolution of physical systems is reversible, that information is never truly created or destroyed, only transformed. Now take that burning library and replace it with a black hole, and ask what happens to the information that falls in. This question, deceptively simple, profoundly deep, is what physicists call the black hole information paradox, and it sits at the intersection of the two greatest theories in modern physics, pulling them in opposite directions, demanding a resolution that neither can provide alone. Stephen Hawking arrived at the paradox in 1974, and he did so by making a discovery that surprised everyone, including himself. Black holes, he found, are not entirely black. They radiate. To understand how this is possible, we need to visit a strange and beautiful feature of quantum mechanics. The vacuum is not empty. In quantum field theory, empty space is not a featureless void. It seethes with activity, with pairs of virtual particles constantly flickering into existence and annihilating each other in time so short that they never become fully real. These are called quantum fluctuations, and they are not hypothetical. They have measurable effects. The Casimir effect, a tiny but detectable force between two uncharged metal plates placed very close together in a vacuum, is a direct consequence of these vacuum fluctuations, and it has been measured in laboratories to extraordinary precision. Near the event horizon of a black hole, Hawking realized something happens to these virtual particle pairs that does not happen anywhere else. When a pair flickers into existence right at the horizon, one particle may find itself just inside and one just outside. Before they can annihilate each other, the horizon separates them. The particle on the inside is captured. The particle on the outside escapes into space. But energy must be conserved. The escaping particle has positive energy, which it carries away from the black hole. The particle that falls in must therefore have negative energy, effectively borrowing it from the black hole's own mass. Over time, this process repeated over immense timescales. Particle by particle causes the black hole to lose mass, very slowly, extraordinarily slowly for large black holes, but steadily, inexorably. This radiation, the thermal glow of a black hole losing mass to quantum effects at its horizon, is called Hawking radiation. And it is one of the most beautiful theoretical results in the history of physics, emerging from the marriage of quantum mechanics and general relativity at the event horizon. But here is where the paradox enters sharp and quiet as a blade. Hawking radiation is thermal. It is, to an excellent approximation, perfectly random. The particles that escape carry no information about what fell into the black hole. They are characterized entirely by the black hole's mass charge and spin 3 numbers, no matter how complex the thing that created the black hole was. Whether the black hole formed from collapsing hydrogen gas or from the complete works of Shakespeare printed on paper and compressed into a singularity, or from a trillion copies of a single specific human memory, the Hawking radiation would look identical. If the black hole eventually evaporates, completely radiating away all its mass over an inconceivably long time, and if the radiation carries no information about what went in, then what happened to all the information encoded in the matter that fell through the horizon? It is gone. And this quantum mechanics says is impossible. Information cannot be destroyed. The evolution of quantum states is unitary, which means it is reversible, which means it conserves information. This is not a preference or an approximation. It is a foundational principle of quantum theory. If information is truly lost in a black hole, quantum mechanics is wrong in a deep and irreparable way. But if information is preserved, if it somehow escapes in the Hawking radiation, then something about how we understand the interior of a black hole must be wrong. Because the causal structure of the spacetime says that nothing from inside the horizon can influence what happens outside. The information cannot get out. The geometry forbids it. Both horns of this dilemma are deeply uncomfortable. And for 3 decades, the greatest minds in theoretical physics argued passionately about which horn to accept. Hawking himself, for most of his career, believed that information was lost. He argued that black holes represent a genuine exception to quantum mechanical unitarity, that the universe at this extreme breaks its own rules. This was not a casual position. Hawking was one of the most rigorous thinkers in physics. He believed the mathematics forced this conclusion. On the other side stood Leonard Susskind, a physicist at Stanford, and Gerard de Hooft, a Nobel laureate from the Netherlands. They argued with equal rigor that information could not be lost, that whatever quantum gravity turned out to be, it had to preserve information. Hawking was wrong. The universe does not cheat. Susskind has written about the intensity of this disagreement with characteristic directness. He and Hawking debated it at conferences and papers in private conversations. For years, the field was split. Brilliant people looked at the same mathematics and drew opposite conclusions. The confrontation was not merely academic. It was, in Susskind's description, a battle for the soul of physics. If Hawking was right, quantum mechanics was not the fundamental law it appeared to be. If Susskind was right, then our picture of what happens inside a black hole based on general relativity had to be revised in some dramatic and as yet unknown way. The resolution, or at least the beginning of a resolution, came from an unexpected direction. In 1997, a young Argentine-American physicist named Juan Maldacena published a paper that would become one of the most cited in the history of theoretical physics. It described a mathematical equivalence, a duality between a theory of gravity in a certain type of curved spacetime and a quantum field theory living on the boundary of that spacetime with no gravity at all. This became known as the ADS/CFT correspondence, and its implications for the information paradox were enormous. If Maldaceno's duality is correct, and the evidence that it is has accumulated steadily over more than 2 decades, then the physics of a black hole in the gravity theory is exactly equivalent to a perfectly well-behaved quantum theory on the boundary, and quantum theories on boundaries are unitary. They conserve information by construction. Therefore, if the duality holds, information must be conserved in black hole physics as well. The black hole's interior, the evaporation, the Hawking radiation, all of it must somehow be consistent with unitarity. Information is not lost. It is encoded, scrambled, distributed, but preserved. In 2004, at a conference in Dublin, Stephen Hawking publicly conceded. He acknowledged that he had been wrong about information loss, that black holes do not destroy information, and that the information eventually escapes in subtle correlations within the Hawking radiation. He paid off a bet he had made years earlier with the physicist John Preskill, presenting him with a baseball encyclopedia, a repository of information, as the forfeit. It was a remarkable moment. One of the most celebrated scientists of the 20th century, standing before his peers saying, "I was wrong." The universe keeps its records. But conceding that information is preserved is not the same as understanding how. And the how is where the story becomes stranger still. If information escapes in the Hawking radiation, it must somehow get out despite the causal barrier of the event horizon. The geometry says nothing from inside can affect outside. So either the geometry is wrong, which general relativity strongly resists, or the information never truly went inside in the first place. This second possibility has given rise to one of the most radical ideas in contemporary physics, the holographic principle. The holographic principle, developed from work by 't Hooft, Susskind, and others in the 1990s, proposes that all the information describing the interior of a black hole, everything that has ever fallen in, is actually encoded on the event horizon itself, not inside, on the surface. Like a hologram, which encodes a three-dimensional image on a two-dimensional surface, the black hole encodes its three-dimensional interior information on its two-dimensional boundary. From this perspective, nothing is ever truly inside the black hole in a way that severs it from the outside. The horizon is not a one-way door through which information disappears. It is a surface on which information is written in a form that is scrambled beyond any practical decoding, but that is in principle there. The interior that in falling observers experience the space, the time, the continuation of their fall, may be in some deep sense a projection. A description that is valid for the observer inside, but which has a completely different and equally valid description from the outside one in which the information never crossed the horizon at all. Here is the part that is almost too strange to sit with calmly. These two descriptions, the infalling observer, experiencing a normal crossing of the horizon and continuing to fall, and the outside observer seeing information encoded on the horizon surface, are not contradictions. They are complementary. No single observer can access both descriptions simultaneously. The infalling observer, once inside, cannot communicate with the outside to compare notes. The outside observer can never directly verify what the infalling observer experiences. This principle that two radically different descriptions can both be valid applied to the same physical situation, as long as no single observer can access both, is called black hole complementarity. It was developed primarily by Susskind and his colleagues in the early 1990s, and it represents one of the most philosophically challenging ideas in modern physics. The universe, it seems, permits different realities for different observers, as long as those realities never directly contradict each other in a way that can be tested. Does time remember everything? The best answer physics can currently give is yes. But in a language so scrambled, distributed across the quantum correlations of radiation, emitted over billions of years, encoded on surfaces, we cannot directly read expressed in mathematical dualities. We are still learning to translate that remembering and forgetting look from the outside, almost indistinguishable. What endures through all of this, through the paradox, through the concession, through the holographic principle and complementarity and the duality that Maldacena found, is a sense that the universe has a deep commitment to honesty, that it does not quietly erase. That even the most extreme process known to physics, even the singularity and the event horizon, and the long, slow evaporation of a black hole over timescales that dwarf the current age of the universe, does not constitute an exception to the fundamental rule that what exists existed. Time in this sense may be the universe's memory, the way that cause and effect are linked irreversibly and completely from the beginning to the end of everything. And if that is true, if the universe truly keeps every record, even the ones swallowed by black holes, then what does it mean for the nature of time itself? Not just near a black hole, not just in extreme conditions, but here in the ordinary flow of moments that carries us through every day. What does it mean that the present moment, this one, the one you are resting in right now, is in principle, written into the structure of the universe permanently, that it cannot be unmade? That question is not physics, or rather, it is physics becoming something else, something that reaches past equations and into the quiet territory where science and wonder share a border. And that territory is exactly where we are going in the final part of this journey. We have traveled a long way tonight. We began with a clock in Bern, Switzerland, and a young man who could not stop staring at it. We watched stars die in fire and silence. We stood at the edge of the event horizon and looked in. We fell through tidal forces that could stretch matter into threads of atoms. We orbited a black hole where 1 hour equaled 7 years of someone else's life. We descended toward a singularity where the equations of physics quietly confessed they had reached their limit. And we sat with the extraordinary idea that even information, even the record of what has existed, may be the one thing the universe refuses to erase. That is a long journey for a quiet night. And now, we have arrived at the last question. Not the hardest one scientifically, but perhaps the one that sits closest to the reason any of us finds ourselves drawn to these stories in the first place. What does all of this mean? Not for physics, not for the equations, but for us. For the experience of being alive in a universe that contains black holes. For the way we understand the time that we are right now moving through. Let us start with something concrete because concrete things are the best bridges to the abstract. In 2019, the Event Horizon Telescope collaboration, a network of radio telescopes spread across the entire surface of the Earth, linked together to function as a single instrument the size of the planet, published the first direct image of a black hole's shadow. The black hole was Messier 87 star, 6.5 billion solar masses, a distance of 55 million light-years from Earth. And the image, that glowing orange ring around a dark central void that appeared on the front page of newspapers and websites across the world, was not an artist's rendering. It was not a simulation. It was a photograph. Light that had traveled 55 million years to reach us, bent by the gravity of something incomprehensibly massive, arranged by the geometry of curved space-time, into a luminous ring captured by a collaboration of over 200 scientists from 20 countries working across 6 decades of accumulated knowledge and instrument development. The team included a young computer scientist named Katie Booman, who as a graduate student had developed one of the key algorithms used to reconstruct the image from the raw telescope data. She was 29 years old when the image was released. The photograph she helped create depicted a region of space so extreme that the light forming the image had circled the black hole multiple times before escaping. When the image went public, something remarkable happened. People who had never thought about general relativity, who had never heard the name Carl Schwarzschild, who couldn't have defined an event horizon if asked, stopped, looked, felt something. That feeling has a name in science communication. It is called the overview effect, borrowed from the experience astronauts describe when they see Earth from space for the first time, a sudden visceral shift in perspective that comes from seeing the familiar made strange from realizing that the things you took for granted are viewed from a sufficient distance genuinely extraordinary. The image of Messier 87 star did something similar for time, because what that glowing ring represents at its deepest level is the geometry of time made visible. The light bending around the dark center is light, following the curved geodesics of spacetime, shaped by 6.5 billion solar masses. The shadow at the center is the region where every path through time points inward. The ring is the boundary between futures that escape and futures that do not. We photographed time itself in a sense, and it looked like a ring of fire in the dark. Now let us pull back even further, because the lessons of black holes extend beyond the physics. One of the most counterintuitive things we have learned on this journey is that time is not universal, that it flows differently depending on where you are, how fast you are moving, and how deep you sit in a gravitational well. That your clock and my clock, under different conditions, tell genuinely different stories about how much time has passed. Most people, when they first truly absorb this, feel a kind of vertigo. The ground shifts. The thing that felt most solid and reliable about reality, the steady, equal, fair march of time, turns out to be a local property, not a cosmic constant. But here is what I find worth sitting with in that vertigo. The fact that time is relative does not make any particular moment less real. It makes every moment more specific, more located, more precisely yours. Your experience of this night, the particular configuration of your tiredness, your thoughts, the temperature of the room, the sounds around you is happening at a specific point in the geometry of space-time. It is your proper time. It belongs to you in a way that is more literal than we usually mean when we say something belongs to someone. The universe, if the information paradox has anything to teach us, keeps a record of it, not metaphorically, as a consequence of quantum mechanics applied to the physics of space-time. This moment is written into the causal structure of the universe, and in principle cannot be unmade. There is something in that which feels against all expectation like comfort. Let us talk about a man named Frank Drake, because his story connects to this in a way that might surprise you. In 1961, Frank Drake, a radio astronomer at the National Radio Astronomy Observatory in Green Bank, West Virginia, organized a small, quiet meeting of scientists to think about a question that most of their colleagues considered too speculative to take seriously: whether intelligent life existed elsewhere in the universe, and whether we might detect it. At that meeting, Drake wrote an equation on a blackboard, 7 terms multiplied together, producing an estimate of how many communicating civilizations might exist in the Milky Way galaxy at any given time. The Drake equation, as it became known, is not a calculation so much as a framework, a way of organizing ignorance, of identifying which questions need to be answered before we can answer the larger one. One of the terms in the Drake equation is the average length of time a civilization remains detectable, and this is where black holes enter the picture in an unexpected way. We have spent this entire journey discussing what happens to time near a black hole. But consider the inverse question. What does the existence of black holes tell us about the time scale of the universe? The universe is approximately 13.8 billion years old. The most massive black holes formed within the first billion years. They have been accumulating mass-warping spacetime and slowly radiating Hawking radiation ever since. When the last star in the universe burns out in perhaps 100 trillion years, the black holes will remain. They will continue to evaporate through Hawking radiation. Over time scales so long, they require scientific notation to write 10 to the power of 67 years. For a stellar mass black hole, 10 to the power of 100 years for a supermassive one. In a universe that will persist for 10 to the 100th years, our current moment, the entire span of human civilization, from the first stone tools to the first image of a black hole, shadow occupies a sliver so thin it barely registers. And yet, here we are in that sliver asking these questions, building the instruments, writing the equations, sending the telescopes to space and linking them across a planet to photograph something 55 million light years away. The universe is under no obligation to be comprehensible, and yet it is. And we are the part of it that is doing the comprehending. Does that not strike you as extraordinary? That the universe evolved over billions of years, creatures capable of asking what happens to time inside a black hole, and of actually making progress toward an answer. There is a physicist named John Wheeler who spent his career thinking about the deepest questions in physics, and who had a gift for capturing enormous ideas in short, memorable phrases. He coined the term black hole, replacing the cumbersome, gravitationally completely collapsed object that had preceded it. He coined the phrase "it from bit" to express his intuition that information might be fundamental to the nature of physical reality, that the universe is at bottom made not of matter or energy, but of information. And late in his life, Wheeler proposed what he called the participatory universe. The idea that the universe is not simply out there existing independently of observation, but that in some deep quantum mechanical sense, observation, the act of measurement of interaction of registration, participates in the creation of physical reality. This is a controversial idea. Many physicists disagree with its interpretation, if not its underlying mathematics. But it points to something that the study of black holes keeps returning us to, that the observer is not separate from the thing observed, that the question cannot be fully separated from the answerer. That time, which we tend to think of as the backdrop against which events occur, may be something more intimate than that. Wheeler himself, near the end of his life, said something that has stayed with me. We are not simply bystanders on a cosmic stage. We are shapers of the universe we inhabit. Let us come back one final time to the clock. Not Einstein's clock in Bern, a different one, yours. Right now, wherever you are, in a bed in a chair, somewhere warm and quiet enough to listen to a story about the end of time, your clock is ticking. Your heart is beating at roughly once per second, a biological clock that is itself a kind of timekeeping device shaped by billions of years of evolution in the gravitational field of Earth, tuned to the rhythms of a planet orbiting a star at a particular distance. That clock runs slightly faster than it would on the surface of a neutron star, and slightly slower than it would in the empty space between galaxies. It runs at the rate determined by where it is in the geometry of spacetime, which is to say here, on this planet, in this moment, at this particular coordinate in the vast curved fabric of the universe. Your experience of time tonight, the feeling of this story settling over you, the way consciousness softens as rest approaches, is a local phenomenon, real specific yours. And simultaneous with it, 55 million light years away, a black hole containing 6.5 billion solar masses sits in the center of Messier, 87 warping space-time, around it slowly evaporating through Hawking radiation, at a rate so small, it would take longer than the current age of the universe to lose a single kilogram. Its event horizon, a sealed horizon of no return, around which every possible future points inward. Both of these things are true at the same time. And they are connected not poetically but physically, through the same equations, the same geometry, the same fundamental laws that Einstein began to write in a small apartment in Bern in 1915, and that we are still more than a century later learning to fully read. What black holes teach us about time, finally, is this. Time is not a backdrop. It is not a container. It is not the stage on which the universe performs. It is part of the performance itself, woven into the fabric of space-time, shaped by mass and energy, experienced differently by every observer, at every location, and yet conserved in its deep structure with a completeness that even the most extreme objects in the universe cannot violate. Time bends. Time slows. Time at the limit approaches something that, from the outside, looks like stillness, but it does not stop. And it does not forget. The clock that fell into the black hole, the infalling observer, crossing the horizon without drama, experiencing perfectly normal seconds all the way to the singularity, their time was real. Their moments were genuine. The universe recorded them, scrambled them into the quantum correlations of Hawking radiation, and will carry them in some encoded form for as long as the black hole lasts, which is, as it turns out, a very long time, almost as long as wonder. Thank you for spending this time with us tonight. Thank you for being curious enough to ask what happens to time inside a black hole and patient enough to follow the answer all the way to a singularity and back. These stories exist because you do. Because there are people who find comfort in the strange, who rest easier, knowing that the universe is larger and weirder, and more beautiful than ordinary daylight tends to reveal. If tonight's journey gave you even a small piece of that, a little wonder, a little quiet, a sense of how extraordinary it is to be a thinking creature in a universe that contains black holes, then it was exactly what it was meant to be. If these quiet journeys through science have become part of your nights, please do leave. Like it helps more than you might think, and it tells us that this kind of storytelling is worth continuing. Subscribe if you haven't already, so the next story finds you when you need it, and share this with someone who might find it someone who looks up at the night sky and wonders. The universe is full of questions this beautiful, and we have only just begun. The next story is waiting. Somewhere in the dark, it is already taking shape, another corner of the cosmos that most people pass by without stopping, that turns out when you slow down and look carefully to contain something that changes how you see everything else. Rest well tonight. Dream gently. And know that somewhere out there, 55 million light years away, a ring of fire glows around a darkness that has been bending time since before our sun was born. Good night,